Robert Zhang will be the first speaker of this session. He's from UT Austin, and he will talk about pure demand operational semantics and program analysis. The floor is yours.
All right, thank you so much for the introduction. I'm Robert Zhang from UT Austin. I'm a first-year PhD student there. Today, I'll talk to you about pure demand operational semantics with applications to program analysis, which is joint work with Scott Smith at Johns Hopkins, where we did the work. Now, before I get started, I will briefly overview how we typically do operational semantics for functional programs. There are typically two approaches to resolving variables. On the one hand, we have the classic lambda calculus, which substitutes variables for values or expressions, depending on the concrete binding strategy. On the other hand, we have these abstract machines that keep track of variable to value mappings by keeping them in environments and then attaching these environments to function values to form closures. Now, very different from both these approaches, our pure demand operational semantics does not involve any environment or substitution. Instead, we maximally compress the machine state by including just two things. One, the thing we're evaluating, whether it's a variable or expression. Two, a call stack, which is just a list of source program points or function applications. It is presented in a big step style, which has some benefits, but is technically not required. A judgment in our system has the call stack sigma to the left of the turnstile, the thing we're evaluating to the right of it, and the resulting value v. Note that there's no environment anywhere in this system. The key idea is that rather than eagerly propagating variable bindings forward, we will look backward along the control flow to recover values for variables. As you will see soon, local variable lookups are pretty straightforward, while non-local ones are challenging and may require re-evaluating certain components. Now, what could this be good for? Well, we argue that since we greatly compress the machine state size, we're able to better support executing programs starting from the middle, because we only need the call stack in addition to the target to jumpstart the execution. This could be good for implementing incremental or resumable interpreters or analyzers, as well as debuggers that can jump to breakpoints. Now, in the second part of this talk, I will go into how we extended our program operational semantics to support a new kind of program analysis that avoids having to finitize domains ahead of time and instead infers recurrences. I would argue that this kind of state compression could be useful for formal reasoning. Now, in the rest of this talk, I will proceed to define our operational semantics, and then briefly go over how we prove this correctness. And then we will briefly talk about the pure demand program analysis, followed by evaluation and conclusions. Now, let's first take a look at our grammar. This is essentially an extension to the pure lambda calculus grammar with a few changes. For example, we define call stack sigma to be lists of call sites or function applications. We also attach these call stacks to function values to form closures, where we replace the usual environment mapping. We use the brain indices to indicate lexical depth for variable uses. For example, the variable y here is a local variable and thus has the brain index 0 because it's bound to its immediate parent function. However, the variable x has the brain index 1 and is non-local because it's bound to a function that's one layer out. Now, in the paper, we first develop a set of rules for based on the pure lambda calculus, but then soon extended to include basic data like integers and booleans, as well as records, which then allow us to encode variants and lists. Again, we are the big step. We assume a big step style with a judgment in that form. We can either be called by value or called by name. The paper uses call by value, but for simplicity, we will present this talk using call by name. It's important to recognize that the conversation of whether variable lookups are eager or demand is completely orthogonal to whether we do call by value or call by name, because the point of a demand-driven system is to not eagerly propagate variable bindings forward. Now, here are the set of rules for our core theory. We have 4 rules here. One rule is to evaluate function values. The other 2 are to look up variables, and we have another one for evaluating function applications. I will now proceed to highlight a few key details. First, when evaluating function values, we will attach the current call stack to it. When evaluating function applications, we will first evaluate the function being applied, E1, and after getting a result back, we will discard the call stack in its closure, and instead push the current call onto the call stack to evaluate the body of the function being applied, which is E. When looking up a non-local variable, we will first pop the top frame from the call stack and evaluate what's being applied there. So it's E1 in this case. And after getting a result back, we will use the call stack in its closure to carry on the lookup of x by essentially hoisting x one lexical level out, which we also indicate by decrementing the brain index by 1. Eventually, though, x will become a local variable at which point we will again pop the top frame from the call stack. But this time we will evaluate the argument E2, whose value will become the result of the lookup. Now, to illustrate, I will briefly walk through a simple example making two consecutive function applications. Let's first start from the outermost application A1, which is highlighted. Now, we can apply the application rule to evaluate what's being applied in A1. In this case, it's another application, A0, which is highlighted. Since it's another application, we will again try to evaluate what's being applied in A0. In this case, it's finally a primitive function, which is highlighted. So now we invoke the value rule to return it while attaching the empty call stack to it. At this point, we're ready to continue evaluating the A0 call by pushing A0 onto the call stack and evaluating the body of the function being applied as highlighted. Since it's a primitive function value, we will return it while attaching the current call stack, which contains A0. Now we're ready to continue evaluating the A1 call. We have essentially finished a recursive call, and we're ready to go back. No, I mean recursive evaluation. Now, notice that we discard the call stack in the closure of the function being applied in A1, which is the call stack containing A0, and instead push the current call, which is A1, onto the call stack. We will use that to evaluate the body of the function being applied, which is a non-local variable x. Now, to look up a non-local variable, remember that we want to pop the top frame from the call stack, which is A1, and look at what's being applied there. As highlighted, A0 is what's being applied in A1. Notice that we have already done an evaluation on A0, but we want to repeat it here to get the same result, but this time we will use the call stack here in the closure to carry on the lookup of x. So we will use this A0 call stack to evaluate x with domain index 0. So since it's a local variable now, we will just, again, pop the top frame off the stack, which is A0, and look at its argument. And the argument is, as highlighted, 0. So 0 will be the result of looking up x. Now, to briefly go over how we proved correctness, we first defined a reference environment-based theory, which is completely standard. We then state and prove that our system is sound and complete with regards to this environment-based theory. To actually do the proof, though, we need two intermediate systems that help get us there, closer and closer to the environment-based theory. We then tie the proof end to end and finish it off. Now, let me briefly go over our extension to a program analysis. We inherit the big step style of the underlying operational semantics, which has the benefit of being more accurate due to the implicit call return alignment at each node of the derivation tree. For a program analysis to terminate, we adopt the standard practice to limit the depth of the call stacks to k frames. However, a novel problem for us is that in order to look up variables, we need to know the fullest extent of the call stack. So in order to recover this full view of the call stack, we try to stitch the current call stack with all compatible k-array stack fragments we have seen so far, which we accumulate in a set on the side as we execute. Our program analysis avoids having to come up with abstract domains to finitize domains. For example, we don't need to come up with these negative, 0, positive domains for integers ahead of time. Instead, we're able to infer finitary recurrences from our big step proof trees and then translate them into constraint horn clauses to be solved for various purposes. Now, to illustrate stack stitching, I will go over a simple example, which is a recursive sum function that breaks down a number into ones and then sum them back up. I've labeled the recursive call as A2 and the overall call as A1. We also have a set S of all the seen fragments so far. For simplicity, I limit the depth of these stack fragments to 2, whereas I limit the current call stack to depth of 1. Now, let's consider looking up variable n with A2 on the call stack. Observe that the fact that A2 is on the call stack means that there must have been at least one recursive call to sum before looking up n. Now, one may attempt to just apply the local variable lookup rule to pop A2 from the top of the stack and evaluate its argument, which is n minus 1. Well, the problem here is that we're left with nothing on the stack while having to evaluate stuff, n minus 1 in this case. So how do we fix that? Well, we adopt a simple approach of trying to match all the seen stack fragments in set S with the current call stack and see which ones match. So for instance, in this case, the two boxed stack fragments are compatible with the current stack because they all have A2 at the front. So we select them and drop A2 from them, and then we're left with these two singleton call stacks. We will then use both call stacks to evaluate the same expression, n-1, and then after getting results from both, we will merge them. Now let's carry out this process. We have two paths to explore, one on the left, the other on the right. The left path is simple because A1 is on the call stack. A1 refers to the overall call, sum of 2. So we're immediately able to look up n from n in this n-1 to be 2 and calculate 2 minus 1 into 1. However, on the right, we have A2 on the call stack. This means that eventually we will reach the same question we have asked before, which is we're going to try to look up n again using the same call stack containing A2. So notice that these are two identical questions. So instead of cycling here on and on, we will be able to terminate, thanks to our state compression, by halting with a stop value. This stop value will be labeled with the current program state, which consists of the variable being looked up as well as the call stack. And now we're able to give a result for the overall lookup of n. This just combines the two results from both paths. On one path we got 1, on the other path we got a stub minus 1. Notice that this overall disjunction is labeled with the same program state as the stub. So with such recurrence results, we're able to translate them into constraint horn clauses to be solved by an off-the-shelf solver like Spacer. This allows us to, one, recover precision at if conditions, because we don't want to always evaluate both branches of conditionals. Well, if Spacer fails to give a definitive answer, we will just fall back to not being precise, where we will just explore both paths. And the other thing is, it allows us to insert custom user-defined assertions along the program. For example, if I want to assert that the overall call sum of 2 gives a non-negative result. Now, I'll briefly talk about how we evaluated our tool. We compared us against two state-of-the-art higher-order program analyses and used the same set of benchmarks to evaluate them. It turns out that we are a bit better in terms of expressive power, as in we infer tighter bounds from expressions without having to let user predetermine those abstract domains. For running times, though, it's interesting to see that we are either much faster or much slower, which may mean that our thing is useful for speeding up program analyzers, but we need to do more work to understand it better. Here's a performance chart to illustrate that. As you can see, it's very fast. Our thing is very fast on standard programming patterns in most of these benchmarks. However, there are a few cases that timed out. That's not shown on the graph here, on the chart here, that involve either non-primitive recursion or exhibit high computational complexity. So examples include the Ackermann and Takeuchi functions. To conclude, we have defined pure demand operational semantics that maximally compresses the program state, and is provably equivalent to standard operational semantics. We also extended by directly finitizing it to become a program analysis that approximates call stacks via stack stitching. It's also able to extract recurrences instead of having to finitize space ahead of time. It exhibits a very different performance profile. Now, if you're curious for more, please feel free to scan these QR codes to access the paper and code, and chat with us and reach us by email. Thank you very much.
Thank you for the very nice talk. I have plenty of time for questions. Who wants to start? OK, I'll start. So I'm not sure this is actually super relevant, but demand analyzer is a big part of GHC, the Haskell compiler. And by demand, the GHC means a blended abstract domain on the absence, whether something is used or not used at all, and strictness. And that allows lots of optimizations like lambda floating, let floating, and whatnot. So granted that, so could you elaborate, is there any relation between your demand semantics and that, or maybe your semantics could be used to prove something like soundness of strictness and absence analyzer?
Well, I gotta say, I don't immediately see a connection. I'm not an expert on the Haskell part of the world, for sure, but I don't think you're talking about lazy evaluation, but that's a big thing for Haskell, and that is orthogonal to us, because as I said, our thing is not really talking about call by value or call by name. We're talking about not propagating variable bindings forward, but I'll have to look into what you said later to give you a better answer, unless other people have a better ideas here. Sorry.
OK, thank you.
Yep.
Ben?
Yes, do you have data or benchmarks for the performance?
Yes. This is showing pretty much most of what we currently support. We use our own DSL that supports only a fragment of the whole set of benchmarks, so we're only able to compute these. If you want to take a closer look.
So anything that the benchmarks have in common in the cases that you're much faster or when you're much slower? What have you learned so far?
Yeah, those would, right. Thank you. That's a good question. I think the benchmarks where we perform very well on, those generally don't involve non-primitive recursions, as in they only use the kind of, the simple recursions that at most mutually call each other, reference each other. And they just do normal recursion with conditionals, with pattern matching, stuff like that. For example, we got examples, we got a rather involved example that involves mapping over a tree by passing in a function. So we're able to handle those pretty fast. However, if you look at this loop-to-one example benchmark, this one involves two mutually recursive calls that are nested in a kind of weird way, in a complex way. So we're much slower than the other two here. So one explanation for our performance profile is that even though we also cache the program analysis based on for example, the expression we're evaluating, the call stack, and the set of stack fragments S, there are still far too many states overall for cache hits to be frequent. So we're still trying to understand the profile better.
Other questions? Yes.
So I'm curious just about asymptotic efficiency.
Mm-hmm.
So like maybe if you have a recursion or something like mutual recursion, you have to look back up in your stack a lot.
Oh, okay. There's one edge case where our interpreter doesn't fare very well, which is long tail recursive call chains. Like if you have an extremely long chain of recursive tail calls, then it means that we will have a call stack that's really long for the interpreter. And we need to keep that in memory. So that's not very memory efficient in that case, which is not what you're talking about, but that's one case. In terms of asymptotics, I don't think we have a definitive answer for that yet. Yeah. It's probably polynomial to like a pretty big. Okay. Yeah.
Yeah.
So
thank you so much. This was a really interesting work. Thank you.
Thank you.
Thanks. Other questions? Okay. If nothing else, I'm going to ask one last question. Any idea how to make that compositional? Because from your benchmarks and your point of comparison, it seems like this is a whole program analysis similar to like what abstract machines do.
That's a good question. Well, since we can theoretically start evaluating in the middle of a program, if we somehow get our hands on the right call stacks for each component, then we can do it. But the question is, how do we get there? I mean, I gave an example of the incremental or resumable interpreters and analyzers. Those are natural examples because when we pause, we can just save up the program state then. But how do we conjure up these different states for different components? That's the question.
Okay, thank you. By the way, if you're interested, why this benchmark is called facehugger and why this one is called MJ01, I can tell you.
Yeah, this is okay. This is drawn from one of your repos, actually. I remember that.
MJ is Midgar Jensen 2009. Anyways, thanks again for the nice talk, and yeah.